I picked up this old Duro bandsaw project from somebody else, and that guy didn't do a very good job of it. He ordered tires, like bandsaw tires, that are not quite strong enough. They kind of, it's easy to move them across the wheel. Also, these wheels are already crowned and the metal is, so I really don't need these tires. I guess they would quiet things down quite a bit, but the problem is that the blade length for this old Duro, 101.5 to 102.5, so 102 inches would be the ideal length there. And that's a little bit harder to find. It's not a standard blade length anymore. So I can understand why he got a blade that's too long. And so he's had to put some spacer blocks back behind there to get this wheel up, which has really thrown things off. So pretty much everything that he did to get this bandsaw working, it needs to come out and be replaced. He had a 1 horsepower motor, which was not nearly powerful enough, and I've replaced it with a Harbor Freight 3 horsepower motor, and that required me to print up this pulley here, which is quite small. And the RPM on this motor is 3,700, something like that, so it's much faster. It's twice as fast as the last one. And with this smaller pulley here going to the larger pulley there, I think I'll get a decent speed out of this bandsaw, like about the speed that I want. Now, in the future, I might 3D print like a side-by-side pulley, so I have 2 speed options. We'll see. But for now, this is it, and I need to do some testing, which means I need to wire up this motor. And this is what I'm working with. I have 10 feet of 10 gauge 4-wire, like 220 wire, soft wire. Now, this is actually repurposed, and currently Home Depot is out of this stuff with no resupply in sight. So must be another casualty of the pandemic. I don't know. So yeah, I'm going to have to get this stuff mounted. Now I only need 3 of the wires. So I've got a 3-wire connector here. This is going to go into a 110 volt, circuit. So there's that. And I've got this nice metal box here to hold the switch. I've got one of these rocker switches, which was pretty cheap. So it's just like a standard rocker switch for your home. You guys have all seen these for turning the lights on and off. And why I chose this style of switch instead of this style should become apparent pretty shortly. The final thing to talk about here is the wire nuts. Yeah, like $2.78. And, this is the classic way of doing it, but I'm not going to use these because I got my lever nuts in the mail. These things are awesome. Just super sweet for doing any sort of home electrical work. I think these are much more prevalent out there in Europe, but here in the United States, we're just starting to kind of see these being used, and they provide all of the, current ability. Like you can pass just as many amperage through the connectors with this as you can with a wire nut, and these are so easy to connect. You just pop the levers up, stick the wire into the hole there, pop the lever down, and you're done. Super, super clean. But these aren't going to work because I'm using 10 gauge wire here, and I guess the lever nuts that I bought are for, 12 gauge and smaller. So I can't get these wires down inside of there, and I'm not about to sort of like trim them down just so they fit into the nut. I guess I'll be using these old twist nut standard wire connectors. All right, I got the switch in the box, all wired up. Got the pigtail here to go to the motor, and this other end goes to a nice 110 volt plug. This whole thing is going onto a bandsaw with a motor that moves, and there's going to be vibrations. And this is a nice sharp metal edge with a wire that can vibrate, cut right into that edge. So that edge will cut right through the the insulation on the wires and short circuit that thing. So that would not be good. So what I'm going to do is 3D print a piece here that pinches these 2 cords, these 2 cables, and prevents them from being vibrated until the metal cuts into them. I don't like my wire strain relief here. You can see it's not centered in the hole. So that means that the wires themselves, this insulation, is pressing up against the side of that metal box. And that's not good. So I need to remake the blue component here to provide proper strain relief to the wiring. This outer plate is going to get replaced by a 3D printed component. I mostly bought this because I needed those 2 screws. This is the first design where the flange here is the same thickness as that metal wall, and this is the replacement where the flange is much more thick. Now the wires are applying constant pressure, pushing this towards the outside, so it's not going to rattle in this direction, but it will rattle up and down in the holes, and that's what I want to prevent. Yeah, that's much better. You guys can see only the blue plastic is touching the metal, and it's really, there's no movement. It doesn't move. It's a little bit cockeyed. That's because of the pressure from the wires inside of there, but I've tested the continuity with a circuit checker, and it's all good. The next thing to do is come up with a custom switch plate, and you're looking at what I came up with in CAD right there. So if I zoom around on this, you can see that the stop sign can pivot around the screws right there, and this thing prints in 3 pieces. Basically, you print this one all by itself, and then you print the stop and that outline. It's just 2 layers thick. So you print that and you leave that on the printer. You don't pull it off the printer, and then you run a separate whole print being the red geometry here. And so the stop ends up being embedded in the red, and it just looks really nice. You can see that the red has this like bumped out portion down here, and that really just helps to activate the switch as I've designed it. And you can see also the geometry for my cable relief over there. Okay, so I've uploaded this geometry to Thangs, and you can scroll around it. Really cool functionality that I showed you guys in Thangs before, and I was able to upload it as a, what is this, a step file, which allows me to, to have this functionality on the Thangs website. Really cool. So this is just available. Just search for stop sign switch, or go to design prototype tests, avatar, or I don't know, username here on the Thangs website, and you should be able to download this and use it yourself. Now, I do need to say that this will only work on that same metal box that I have. So head into Home Depot, which is where I got it, and I'm sure they're going to have that same box in stock, and so you can get that. But if you don't have a Home Depot near you, I don't know. It's kind of a narrower, metal box. So that whole plate there isn't gonna. I don't know. I don't think it's gonna be largely compatible with other things. Now, the key here is that these switches are available elsewhere. Look at this ready-made version of it. Enclosed plastic box, big old stop sign. I don't think that looks nearly as nice as mine does, but it's got all the functionality. The wiring is a lot smaller, so you're not going to be able to put custom gauge wiring in there. I don't know how many amps this is rated to, so you've got issues with these. Also, a big old price tag, $51 for that one. Here's a cheaper one, also coming from California, for only $15. And of course, you can get one for $10 plus $5 in shipping. Same price from China, and you've got to wait 45 days for this to get shipped to you. So if you want it today, you can just 3D print your own. And for all of the components, the metal box, the decorative plate, that goes over the switch, and the switch itself, I paid $5.50. So it is quite the savings, and I think it looks better. So DIY or buy, in this case, I think DIY, because it gives you, not only does it look good, but it also gives you the option to increase the wiring gauge, which makes things more safe. I think that this silk style of filament looks really cool. It gives it that sort of, reflective stop sign look to it. This is meant to be printed in one go, but I printed this up on my this little Core XY machine that I've got, and it doesn't currently have part cooling on it, which means that I had some pretty severe problems with part peeling. So these ears here, I had to reprint and then just use a soldering iron to sort of blend them into the original print that I had cut off. All right, it's all done. Let's show these guys what we're working with. I used some Sharpie to color the top of the switch green, the bottom of the switch red. I've 3D printed this part here and the stop sign. And hey, buddy, will you show these people how it works? Yeah. Okay, hit the stop sign. Turn it back on. There you go. And that's as simple as that.
I think it's good to have. I want to have one of these. I need to make something with it.
Okay, but this doesn't make things. This just turns the machine on that makes the things. So maybe you can use your 3D printer to make things instead.
No, the other bundle that you gave me, it doesn't work.
The printer I gave you doesn't work?
Yeah, so that's why I want this.
I understand. Well, I'll tell you what, I'll make one for you.
Of this?
Yeah.
Oh. Now, Dad?
Yeah.
Can you draw green and red because I love, and can you put a top sign on there? Because I love the top sign and the switches. And I love the pipes and the wires.
Uh-huh.
So I want you to make it just like the wires and the tubes.
Okay, I'll do my best.
Okay, do your best.
Thanks, buddy. Ta-da! There it is, working fantastically. It's a little bit noisy, but here, I'll turn it on for you guys. This is right there at my knee height. This is the quality of cut that I'm getting. Pretty good. Brand new blade. This is this like hybrid style blade that I got from McMaster car. And you can see that I'm running this on the stock wheels, you know, the old metal wheels that came on this thing. They are crowned. They're metal and they're crowned, so they're going to be kind of noisy. But the tires that the previous owner who tried to renovate this thing put on the machine don't really stay on it, and they're wider than the actual wheels, and they migrate because this is already crowned. So the tires themselves are crowned, and so you got a double crowning thing happening, which isn't good. So I'm just going to leave it real noisy like this. I could stretch a bicycle inner tube across the wheels here, but the problem with that is I would not be able to cut metal. And I do plan on cutting aluminum from time to time. This blade is supposed to handle both wood and aluminum. Here we go. So you guys just saw me really bog down the blade and bring it to a near stop, which is really taxing on the motor. And if I was going to trip the breaker, that should have done it. So here's the saw, and there is the 20 amp circuit breaker in the box. There's the plug, but the line is longer than from the box to there because it goes down there somewhere. So we've got a good 20 feet of wiring inside the wall on top of the, 9 feet of 10 amp or 10 AWG wiring here to the saw itself. And here's the manual that came with the motor. So the wiring diagram for this one, the 3 horsepower motor, is that. And you can see this is meant for 230 volts, while I'm running it on 120 volts AC. And a quick note about that, 110 volts AC was the original standard proposed by Tesla, Nikola Tesla. And Westinghouse, who was then embattled with Edison, he eventually won. The Westinghouse Tesla version of AC power delivery to homes won because it is the superior way to do it. But Westinghouse wanted it to be 133 volts, which is funny. So yeah, there's always been kind of arguments over the nuances there. So in America, we now have between 110 and 120 volts AC coming out of most of our outlets, although you can get 220 volt AC to your shop, and they even have 3-phase 220 volt, which is Nikola Tesla's baby. That was his invention, and also the better way to run things, which is why the best shop equipment always is 3-phase 220. So yeah, this motor designed for 2-wire 230 volts, so not 240, 230 volt AC, and yet I've shown that it's working just fine on a 20 amp 120 volt circuit. Why am I not having big problems? And also, am I getting half the power out of that motor because I'm only feeding it half the voltage? To answer those questions, we've got to fall back on the most basic equation in electricity, and that is voltage times amperage equals wattage. This motor, we know, is supposed to run at 230 volts. If we look on the website, we can see this is rated at 12.26 amps, which gives us a wattage of rounded 2820. Now, the thing to understand about an electric AC motor is that it pulls electricity through the circuit. It doesn't get pushed by the electricity. So you can't decrease the voltage and think that the amperage is going to stay the same and therefore the wattage is going to decrease. That doesn't work like that. The motor is going to demand all the electricity that it's rated at. So if it's rated at 2820 watts, that's how many watts it's going to pull, no matter if you're running it at 230 volts or at 120 volts. So if we change the variable, 120 volts here, and we multiply that by an unknown amperage equals 2820 watts. Well, we can just divide 2820 by 120 volts to get our amperage, and that comes out to be 23.5 amps. That is more than the circuit is rated at. The circuit's only rated at 20 amps. So not only are we exceeding the rating of the circuit, at least the rating of the circuit breaker. Like, I don't know what wiring they put back there behind the wall of the, the Romex cabling going from the circuit breaker to the plug. I did use some very stout 10 AWG 10 gauge wiring from the outlet to the saw. So, but who knows what the wiring is? Who knows what the actual circuit can handle? But the circuit breaker itself is rated at 20 amps. And the general rule of thumb is you only want to get to 80% of the 20 amps. So really, we should only be at 16 amps. And we are basically 33% above that. The general principle of a circuit breaker is that you have two metals and they're bonded together. And one of them expands more in the heat. Putting electricity through a circuit will heat up the wires in it. Before they get red hot, they do expand quite a bit. So if we bond two pieces of metal side by side, one of which expands more than the other, then what will happen is you'll get a bend. See, because as this outer one here expands more, it's got to travel a further distance than that. And so, we can't, it's going to warp over. And you basically can have like a contact point here, and as it expands, it goes away from the contact point. And so you no longer have electricity flowing. There's no place for it to flow because it's not making contact. So it takes time for the metal to heat up. So that can explain why instantaneously we don't just trip the circuit as soon as we try to draw these this overrated voltage through it, or overrated wattage, I should say. And that's actually a good thing, that it doesn't instantly trip the second that you draw more wattage than what it's rated for, because electric motors on startup, they have a really high power draw. So if this is the time and this is the draw, they start off way higher than what they're rated at. And that very quickly diminishes in like a parabolic fashion as the motor speeds up. As it gets to, like, let's just say about there, it's at full speed and it's going to draw the rated 2820 watts, across there. But, until that, there's a spike, and this spike doesn't last very long, but it's definitely there. And so you wouldn't want your circuit breaker to instantly trip the second that you drew, instantaneously more than the wattage. So the fact that there's a delay on that is a good thing in general, but I'm definitely abusing that circuit. And even though the circuit breaker's not tripping, like I said, we don't know the wiring that's in the walls. So that means that I could really be like overheating, just like the circuit breaker gets overheated. The actual wiring in the wall could be heating up and it could catch on fire inside of the wall cavity. Back to the 80% rule, I really don't want to be running this over 16 amps. So I absolutely must run this motor on 230 volts or 240 volts AC to do it right. There's nothing reasonable that I can do to lower the draw of the motor. It's fundamentally built into the motor that it's going to demand 2820 watts, which equates at 120 volts to 23.5 amps. I can't do anything to lower that draw of the motor. I need to put a different motor on there, and the different motor that I had on there previously wasn't powerful enough. So in order to have the power that this saw needs, this 3 horsepower is really quite nice, and it just means that I need 240 volts. And we can see there's actually quite a number of 240 volt circuits. The range top, all of these heaters, there's radiant ceiling heat in this house. We've got the, I don't even know what these are. So yeah, all these, the dryer, all these are 240 volt circuits, but unfortunately every single slot in this panel is taken up. Normally, you'd have some empty slots, and I'd be able to, if I had 2 of them, I could easily just wire in an outlet, stick an outlet right here or right there with 12 inches of wiring to plug the bandsaw into. And I can't do that because this is not my house. I rent here, and the landlord has not really been thrilled about the idea of changing up the wiring. He just, it's a nice house, but he doesn't want to make any changes or help me out in this regard. So, is what it is. Here's the thing, you guys. I just ran all of these cuts. These are ripping cuts. So they should be like harder for the saw to handle than cross grain. And I ran all those cuts back to back. At the very end here, I pushed until I bogged the motor down to a full stop, and that did not trip the breaker. Then I came over here and I turned my air compressor on, and I did these cross cuts, pushing really fast until I stalled the saw out, stopped the blade, which is, stalling the motor, and it still didn't trip the circuit. So, it took me a few minutes to make all of these cuts, and I'm not seeing an actual real life problem here, especially given that I could run the air compressor on the same circuit, and that's going to be drawing a significant amount of power. So, why am I not tripping that breaker? It's kind of a mystery. And one possible explanation is that this could be one of those very rare instances where low quality Chinese components is a good thing. So they claim those wattage numbers, and they could be 25% lower than what they're claiming. And of course, that would mean this is only a 2.5 horsepower motor. But hey, it's doing the job. It's actually cutting quite nicely, and it's not popping the circuit breaker. So I don't have to sweat it that I don't have the right 220 power going to the saw. Now, my final option here that I could do is one of these heaters I don't use. Like at least one, there's a heater in the laundry room that we don't use, ceiling heat. I don't know if it has its own circuit or if it shares a circuit with another room. But look, there's a heater here. There's like 1, 2, 3, 4. Maybe there's 6 heat zones. It's hard to tell. So maybe I can use one of those heaters that we don't use. So when the box says 230 volts only, could be that the engineer who designed this motor knew that the maximum circuit you can get for 120 volts AC in America is a 20 amp circuit. And, he did the math too and knew that, the 23.5 amps is what was going to be required, with a 120 volt circuit. So that could be why it says this. Or it could be the wiring right here. So the wiring going into the motor itself. Now, you can see my white wire right there has 2 wires going into it. But the other wire, the black wire, the 10 gauge, only has a single wire coming from it. And that's dropping down significantly inside. I'd say that's about half the wire gauge there. And then, of course, there's the actual coils, the windings on the motor itself. And maybe those can't handle 23.5 amps. Also, what about this switch? This is a 15 amp switch, and I'm currently running 23.5 amps through it. So if I can get 240 volts into the saw here, then this will only be running at 12.26 amps, which is well below the rating of the switch, and everything will be good. But sketchy as this whole electrical experiment has been, the only casualty has been this PLA pulley that I made. All right, what happened with this pulley here? It's not too hard to figure out. Basically, it's too small. So all these V-groove pulleys have a V shape to them, and that corresponds with the V shape on the belt here, if you took a cross-section of this belt. So as the belt sits into the groove, it's wedging against the walls of the pulley. So the actual bottom of the pulley doesn't engage with the belt. It's actually the walls. And with this belt here, you can see it wants to spring open. It doesn't want to stay in a nice tight form around that pulley. So the belt itself is trying to disengage from the pulley. Now, the weight of the motor is kind of forcing it around there, but it's not great. Also, because there is just a small pulley here, we don't have much of a contact patch for that belt. See, the contact patch is always going to be half of the circumference, roughly speaking, half the circumference of the pulley. And in this case, being a really small pulley, that's a really small contact patch. So a larger pulley would make for a larger contact patch. I suspect that even if I got a metal pulley here at this size, I'm still going to get that slippage, which will not destroy my pulley because it will be made out of metal instead of PLA plastic, but it will destroy belts. So what can I do about this? Well, my first inclination was to reprint the part with some carbon fiber impregnated nylon filament. I've got that fancy all metal printer going, and hey, I can get really fancy and make a much more structural pulley, but this was never supposed to be a final product. This was a test to see if I liked the saw speed with this small of a pulley. And more than that, it revealed the fact that I'm going to get slippage on a tiny little pulley like this. So I could redraw this pulley. This is the one that you're looking at right here. And I could make it bigger. So let's say this one, for instance, and I could print it with even, hey, let's go with really high temperature. What is that? My polycarbonate. And I've even got carbon fiber polycarbonate. That's pretty fancy. It would probably survive. It would probably do just fine. But that's some expensive filament. That is quite a bit of work to slice that and to make sure I'm not going to get any bed warpage. Now that the part is a little bit larger, I could potentially have it peeling up off the bed. I don't have a heated chamber yet. So yeah, it's a lot of work. And why would I do that work when I can just go online and order the part for $8.58? So yeah. So I'm not here to reinvent the wheel, you guys. 3D printing is awesomely empowering, but it doesn't mean that when your only tool is a hammer, everything looks like a nail. Well, this is not a nail. This is time to get a metal pulley, that's going to stand the test of time and that we know will work. Now, looking at all these circles up here, you can see I was playing around with pulley diameters and trying to get an optimal gear ratio. I do like the way that this was cutting. It was pretty good going through wood, and the stock gear ratio there, 3,628 surface feet per minute, SFPM, SFM, surface feet per minute. So yeah, that's pretty decent. So right around 3,000, it looks like, is what I'm aiming for. And looking at the forums online, a lot of guys say that that's the optimal speed for cutting through wood. Now, I do have to say that after the research here, I set out this project with the goal to be able to cut both wood and aluminum with this saw, but it's not going to happen, you guys. 3,000 surface feet per minute is too fast for cutting aluminum. So I'll have to probably get a secondary small bandsaw for cutting both steel and aluminum. Okay, so the wheels of the bandsaw, the actual wheels where the saw rides, the saw blade touches, are 48.858 inches in circumference. So I can basically multiply the RPM by that and get my surface feet per minute. And so after doing all the math, I figured a 2.85 inch pulley would give me a better contact patch than this one. So it would be decently sized. And going with the very large 12-inch pulley attached to the saw gives me about 3,300 surface feet per minute, which is a little bit high. I'd like to be lower than that. And so I think I can get away with a 2.5 inch pulley instead. So a little bit smaller, which should give me right around 3,000 feet per minute, or surface feet per minute on that saw speed, the actual blade speed. So I think this is going to work out. Unfortunately, I have to wait for these pulleys to come in the mail. All right, so where to from here? Well, I need to get an electrician out to the house to potentially put a 240 volt plug right there underneath the circuit breaker box. I've wired houses up before, but those were houses, well, pretty much one house that I owned and another house that the landlord gave me permission to wire up when I was working in the construction industry, and I had electrician friends to really advise me on that job. So I could do it. I know what needs to be done, but yeah, it's got to be above board, licensed, bonded, and insured. So that's something I'm going to have to wait for, and it's like a 2-week wait, I think, at least, maybe like a month out until you can get an electrician to come around, because the trades are in high demand these days. So that's going to be a while. I'm going to get my pulleys here next week, it looks like, in the mail, and yeah, if I can't get this thing rewired, I guess I'm just going to install a different motor. I'll go to Harbor Freight and get the smaller motor that will not trip the breaker, although this one isn't tripping the breaker, and I don't use it very often, so I might just keep it the way that it is, you guys. Unsafe and as violating of the numbers as it is. I'm not going to do any major projects with it until it's wired into 240, but yeah. All right, well, that'll do it for this video. We're going to leave it here. Thank you, big thank you to my Patreon supporters. You guys keep me making videos. Without you, I would surely quit. And I will see you on the next one. Thank you for watching. Goodbye.